Welcome, everyone. Today we're going to talk about instrumentation, and Ken and I have noticed over the years as we talk with customers, some common questions come up. One of them is that we sell a lot of load cells, and not so many people buy instruments necessarily with the load cells. And the question would be, well, what are they doing then? And in some cases, customers already have their own data acquisition or instrumentation. In some cases, they just haven't really considered it. Sometimes they're mechanical type guys, so they're worried more about the load cell and not so much about the instrumentation side of things. So there are some advantages to having an instrument and a load cell together. One of them is that they, are not guaranteed, but they're intended to work together as a system. Whereas if the instrumentation is purchased separately, it may or may not be suitable for that specific load cell. Also, maybe some issues as far as how you get the instrumentation set up. When they're purchased as a pair, everything's set up and ready to go. So one thing an instrument does when used with the millivolt per volt based sensor is it provides a nice stable excitation voltage to the sensor. Wheatstone bridge sensors, like a load cell, requires excitation voltage to operate. Basically, you apply 10 volts input, and then you have an output that's directly related to the input voltage. That voltage output is going to be a millivolt signal per volt of excitation. So typically, a load cell is going to be rated with an output of, say, 1, 2, 3, or 4 millivolts per volt. Typically, an instrument is going to provide excitation voltage to the load cell of around 10 volts. Some may go as low as 2.5 or 5 volts, though, depending on the instrument. So the load cell signal is in millivolts per volt. And what that means is, for example, if it's a 100-pound load cell rated at 2 millivolts per volt, if it has a 10-volt excitation, then you get 2 millivolts output per volt. That equals 20 millivolts. So at capacity, you get 20 millivolts output. At no load, you get approximately 0 millivolts. And it's linear. And there's always some type of a zero signal. So instead of, say, exactly 0 millivolts, it might be 0.1 millivolts. And then the output as 2 millivolts per volt means you get a change in output of 2 millivolts per volt. And so you might go from 0.1 to 20.1 millivolts per volt. And then most instrumentation will have the ability to zero out that zero signal to make it exactly 0. So as far as types of instrumentation goes, first off is the signal conditioner. What this does is it provides a stable excitation voltage to the sensor and then takes the signal from the sensor and amplifies it to a higher level output, such as plus or minus 5 volts, plus or minus 10 volts, or 4 to 20 milliamps. The signal conditioner usually includes some kind of filtering, maybe a lot of filtering or just a light filter, but typically there's some filtering involved. They're typically analog devices, which means they don't have sample rates or any kind of digital conversion. So they're typically just taking the signal, amplifying it, and outputting. Many data acquisition systems that customers may have require higher level inputs, such as plus or minus 10 volts. And so the millivolt signal from the load cell is typically going to be too low to work well with most data acquisition systems. Now, there are certain data acquisition systems that do have, actual load cell or strain gauge bridge channels. And in that case, those ones would be suitable for bridge sensors like a load cell. But in many cases, they're really looking for something like a 10-volt input. Also, a data acquisition system doesn't necessarily supply a stable excitation voltage to the sensor. So if you did have a data acquisition card or system that's able to measure millivolts very precisely, you still have to worry about supplying an excitation voltage to the sensor. And if the excitation voltage floats around the ball, you see that directly in the output. So that's not good. When selecting a signal conditioner, some things to consider are what power supply is available, how much filtering you think you might need. If you're not sure what filtering you need, you may want to have something that has adjustable filtering. Also, the input range of the signal conditioner. For example, if you have a 4 millivolt load cell, you want to make sure the instrument isn't limited to 3 millivolts per volt input. Also, the scalability of the signal conditioner. Sometimes you may have a 100-pound load cell, but you really want 10 volts out at 5 pounds or or 50 pounds, is that possible? Some signal conditioners will allow you to do that, some will not. Also, zero adjustment range. Typically, they all have a limited amount of zero adjustment. In some cases, for example, in a weighing application, you might have a heavy platform you want to zero out. That would require a lot more zero adjustment. Some instruments will allow that, some will not. Next off, we have something called a PC interface module. This is a signal conditioner that also combines analog to digital conversion, and that then allows the signal to be transmitted digitally to a PC. Popular interface modules either connect to a PC using USB, some of them may be wireless USB, or even Bluetooth for the data transmission. Typically, these type of modules will be provided with the included software, and the software will typically allow display of the data in engineering units such as pounds or newtons. They'll allow logging of that data to a file, and sometimes they'll also include graphing capability. The files are typically in a format that can be opened using Excel. Basically, these type of modules are nice if somebody wants to log data into a PC, but they don't already have a full-feature data acquisition system. Sometimes, too, even if they do have a data acquisition system, these PC modules can be quite nice because they're just easy to use. You don't have to understand the software involved with the data acquisition system. You don't have to get into any of the programming. So one of the advantages of these modules is that they're plug and play typically too. So basically, you buy the system, you plug it into the PC, all the setup is already done. Just fire up software, it's ready to go. Considerations when looking at a PC interface module would be how many bits resolution. Is it enough? Most times they'll be more than adequate, but that's something to consider. How many channels do you need? What sample rate per channel, and also features of the software and what type of output. For example, if you want wireless output or if you want a USB connection to the PC. Indicators, digital instruments. These are items that provide an actual physical display. They include the features of a signal conditioner, that they provide stable excitation voltage load cell, and they convert that sensor signal to a digital display. Some of these displays will also have analog output. So it's like a signal conditioner, except it has a display on it, and then that signal can then be sent off to a data acquisition system. Sometimes they'll have digital outputs, either USB or RS-232. They'll typically have some kind of digital filtering that's selectable. They may monitor peak and valley. You can look at, say, press force or impact loading, certain things that may generate a peak or a valley. And they also have set points that can be used to trip relays or start and stop motors or alarms. Things to consider when selecting an indicator are what is the internal sample rate of the indicator, or what is the update rate of the analog output. We also talk about sort of hybrid solutions that may include features of signal conditioners as well as analog output or interface to a PC. We have here just a little list that lists instruments and interface provides, and some of them have indication capability, some of them have analog output, which would say signal conditioner. Some of them can connect to a PC, some of them have software for graphing or logging. We have here is a diagram showing basically the same thing, but a different way of representing it. Some of these systems have features that include indication, signal conditioning, and PC interface. Some of them do only some of those things, some of them only do one. Okay, I'm going to pass it over to Ken now.
Keith did a fine job of explaining the different types of instruments that we have. And what we'd like to do now is go through a few applications and show you how to select the proper instrument for your application. I've put on the screen here an example of an instrumentation worksheet. Basically, what this represents is the type of questions that an interface applications engineer would ask you when you called in requesting a certain type of instrument. It's a nice tool for you to have in your repertoire so that you can be prepared and make sure that you've gone through the full thought process before you're ready to pick an instrument for your application. Now we're going to go through a few different scenarios of applications. The one that we put on your screen now is a customer mixing application. What the customer is trying to do here is put together an end product which is made by mixing raw materials together in a tank. And it's important for the customer to make sure the quality is correct and it's made safely, is to make sure that they're mixed properly without under or over mixing. And to do this, as represented on this diagram, it shows a number of different components to come up with the solution. So our model 5330 reaction torque transducer is used in coordination with the mixing motor. And then the customer's goal is to actually control the mixing through a DAC or controller of their own. And the challenge here is to come up with an instrument that will communicate between the reaction torque transducer and the DAC controller. So using the instrument worksheet, we've gone through and completed this. Customer, I'm going to pick a few key bullet items off of it. Total error customer's looking for is 0.5%. They have 18 volts to supply to power the sensor. They're looking again for reaction torque, which has a millivolt per volt output, but they do need this to communicate a signal of a high level to their DAC or controller, which is plus or minus 10 volts. So based on that, the best match for it was our model STA. And there's a picture of the solution that we chose. So again, the millivolt per volt signal will go in this STA, and what will come out of it will be plus or minus 10 volt. We'll scale this at the factory for the customer, make sure that 10 volts represents, in this case, 600 inch-pounds, and they'll plug it right into their vac when they get it, and be able to work with it and control the mixing operation. I'll turn it over to Keith.
All right, for the next application, we're talking about a bolt clamping force study. This would be done in a lab, and the customer doesn't necessarily have any data acquisition system set up. So what they want to do is they want to study the amount of torque applied to a bolt and how that relates to actual clamping force in the joint. Because they don't have a data acquisition system, but they would like to log data so they could study it later, they may recommend using something to interface to a PC, such as a PC interface module. Go through the worksheet. One of the things you might ask is, what type of instrument would they need to determine that they don't already have instrumentation. They really want something that stands alone. They want to be able to log to a computer, possibly create graphs. So an interface module is appropriate. What we recommend, or what we might recommend in this application, would be something such as our INF USB, which is quite basic signal conditioning. It connects to the load cell, plugs into the PC over the USB power, is provided over the USB, so there's no other connections that need to be made, and basically comes with software that allows for data logging and visualization. We actually have a video of the INF USB software in action. What this is going to show is the software in action. Also going to take the opportunity to demonstrate the sample rate. What I've done is I had a load cell hooked up to the computer, and I applied an impact to the load cell. Initially, the sample rate was set at, I think, a couple hundred samples per second. We have a peak value recorded. I then go ahead and increase the sample rate to 2,500 samples per second and do the same test. You can see the peak recorded is quite a bit higher. So here we go. The software allows you to set up scaling, so you can use it with different sensors. You just have to adjust the scaling each time you apply a sensor. You can do some averaging to smooth out the response. You can also choose the sample rate. And then there are some triggers to start and stop recording data if you so choose. I'm going to go ahead and start the test now. Initially, we want to reset the peaks and the valleys. Start the test, apply our impact. You can see the graph self-scale, so as soon as the impact is applied, the graph finishes. And you see the peak is only 1.47 newtons, which you might think, oh, that's not quite as much as I expected. Well, turned out it's not nearly as high as it should have been. So go back, change the sample rate to 2,500. Do the test again. You can see over here in the right corner, the peak was actually 161 newtons, so quite a bit higher. You can see the peak was recorded. And so that shows a bit of how this software works and also the difference between certain sample rates. Now, we can't say that 2,500 was necessarily required for this application. It could be 1,000 hertz would have been fast enough, but I think we can say for certain that a couple hundred was not enough. All right. Here's the video. Next application, I'm going to turn it over to Ted.
Hi, everyone. Now we're going to talk about another application. This is a tank weighing application where our customer basically wants to monitor weights to see if the tank is full, empty, or when they dispense by weight. And so we took a look at our instrument worksheet, and a few highlighted areas of this application detail is that this is going to be an outside application. And so we need an indicator. The customer wants to see the readings right at the site, as well as they want to send a signal to their control center. So again, an outside environmental casing is required for this indicator. And they're going to use more than one load cell, so we're going to make a note of that. And also, when sending the signal to the control center, they're going to want plus or minus 10-volt output. So what we're going to need is a hybrid indicator instrument that has analog output and also can display at the site. And then in addition to that, since we're using multiple load cells, one of our questions on our worksheet says you'll need to use our JB104 junction box. So a junction box actually takes multiple load cells, puts them together into one box, sums the signal, and sends one signal to the indicator so that it can produce one total measurement. And so let's take a look. Yes, we need an indicator. And our model 480 is the choice because it is a stainless steel enclosure. In this application, it's used in compression only, but this indicator goes in both tension and compression. And then again, as described before, we use our JB104 SS junction box to combine the signals together. And here's what they look like. And in the end, the analog output of the from the displayed reading would also be sent to the control center in a plus or minus 10 volt signal.
All right. The next application we're going to talk about is another R&D application where a customer is interested in being able to measure fluid flow using change in weight by hanging a bag on a load cell. And you can imagine the bag is something like an IV bag, and they're measuring the flow of the fluid into a patient. An operator may sit there and adjust a valve or adjust the fluid flow. They want to be able to see a local display of what's happening, but they also want to be recording data to a PC for later use. So go through the application questions and you come up with, they need a certain accuracy. It's going to be an indoor application in a lab or in a hospital room type environment. So there's not going to be any sealing involved. Since it's R&D, the equipment won't have to be sterilized or anything afterwards. It'll be just limited use. And so we come up with something like a hybrid device where you have a display that's local right at the test site and then also logged into a PC. And something like that might be our model 960 with software that comes with it. 9860 is a display. It displays in engineering units, and then it also has an output that can be logged into a PC. 960 has some nice features I'll mention since we're talking about 960. One of them is TEDS. We haven't mentioned TEDS yet, but TEDS is something called Transducer Electronic Data Sheet. And what that does is it allows a chip in the load cell to identify to the indicator what type of load cell, what capacity, what the output is of that load cell, and then the instrument can self-scale. So basically, when you plug in a TED load cell to a TEDS capable instrument, the instrument scales itself for certain defaults that are loaded into that chip. So it's nice if you have multiple sensors. You can plug each sensor into the same indicator and have it scaled for you without having to fiddle with the settings. The other thing about this 960 that's nice is if you're going to be using an analog output from an instrument, this system passes the analog output straight through an amplifier and out the back and does not go through the analog to digital conversion process. So it's quite fast. We have 1,000 hertz bandwidth on the analog output, where many indicators, the bandwidth of the output is limited by the A to D rate. In this case, 230 readings per second is quite fast for a digital indicator, but still would be limiting for the analog output. Peak and valley monitoring is handy. Look at peaks and valleys, they can be reset. Okay, we can address a couple of questions now. Tear is basically a zero feature. Sometimes a tear is recoverable in that you can press the tear button and get a net reading, and then when you press it again, it goes back to a gross reading. Imagine if you had a scale and you had a box on the scale, and then you wanted to fill the box with, say, chicken. Initially, you put the box on the scale, and the scale reads, 1 pound. Then you can press the tear button, and the scale would then be reading 0. Then you put 10 pounds of chicken in. And then if you were to go back to the gross weight, it would be 11 pounds. So the gross weight would be 11 pounds. The tear weight would be, or teared weight would be 10 pounds. So the tear button is just a nice button that allows you to perform a tear operation. Load cell instruments may typically have that feature. Other instruments that are more general purpose may not. You have to actually go into a menu setting to adjust that. So it's nice to have a button right on the front panel. Shunt calibration. A load cell is a bridge, outputs millivolts per volt, and that signal then is taken down stream, converted through a signal conditioner, indicator, maybe into a data acquisition system. So everything downstream of the load cell needs to be scaled. A handy way to scale the instrumentation downstream of the sensor is with shunt cal. Shunt calibration basically takes a resistor of known value and connects it across 2 legs of the Wheatstone bridge of the sensor. And every time that same resistor is applied to that same sensor, you always get the same output from the sensor. So the resistor is chosen to make that output somewhere in the within the capacity of the sensor, typically about 75%. So a 100-pound load cell the resistor is chosen to give a signal equal to about 75 pounds. What happens with that then is you can apply that resistor, and you know that's equal to putting 75 pounds on the load cell. And you make sure everything downstream, including your instrumentation, your data acquisition, is all scaled and reading properly. So it doesn't really check the load cell per se, but what it does do is check everything downstream of the load cell. Again, a 100-pound load cell may not be that difficult to apply a 75-pound weight, but it may not be real convenient. And then if you're looking at, say, a 100,000-pound load cell, much more difficult to apply a 75,000-pound weight. So a button on the front that allows shunt is an easy, quick way to check that things are scaled properly. All right, we got another video showing 9860 in operation. Okay, this video demonstrates a couple things. One of the things that we have, let's see. One of the things that I may have mentioned is digital filtering. We have a sample rate on an instrument. Those signals are being basically converted to digital readings and then displayed. You don't necessarily want to display every one of the readings because there may be noise associated with that. So there may be some digital averaging being done, digital filtering. There's a trade-off though. When you have heavy filtering, you get a nice stable reading. What then you have is slow response. And so one feature of many instruments would be, at least some instruments, would be a collapsible filter. What that allows is quick step response, but also heavy filtering. So initially the filtering is going to be set basically off. You're going to see that the display is a little noisy, and then we're going to set it to rather heavy filtering, and that shows that the display is quite stable, but shows a slow response to a step input. And then later we'll select the collapsible feature to turn the filter off if a step input is seen, and then you'll see a quick response with also a very stable reading afterwards. So we'll play the video now. So this shows the software. See some of the features. I applied a weight, jumped up to 600 something, but it seems a little noisy. The software also allows unit conversion. And so we've got pounds displayed. We can convert to newtons. Can show peak, valley, instantaneous readings. You can program the meter using the software. It's quite nice. If you want to change the filtering or the set points, you can do it pretty easily with the software instead of having to go into the menu settings. What we have now is just change it to a fairly heavy filter. And now we're going to drop a weight onto this sensor. And we'll see that it takes quite a while to respond. It is nice and stable when it gets there, but it's somewhat undesirable for it to take so long for the reading to stabilize to its true value. So we're going to go back into the settings and change the band, which is basically defined when the filter is active. Change it to a lower value. Now this will allow the filter to collapse as we apply the weight, and then it'll turn back on once the reading is where you want it to be. So you see it pops right up to the reading and then pops right back down to zero when you pull the weight off. Pretty nice feature. Software is also capable of logging data to a PC. It will log either peak or the valleys, or it'll log instantaneous data. All right.
To introduce you to a new product of ours. It's our WTS wireless telemetry system. What we can do is for applications where customers have long runs where cables could be a problem, we have an instrument that can connect to the load cell and take the readings from the cell, then transmit it through wireless means and be received into a PC or a handheld display for use in the application. Some of the advantages are it's pretty easy to use. It's capable of receiving multiple inputs, up to 100 channels. It's compatible with all of our force sensors and other company sensors as well. We can calibrate it, test it, and have it ready to run for you after you purchase it. And you could have usage up to 3 months using AA batteries. We're going to, so that kind of encompasses the slide that I just went over. System looks like this, where the item on the left is a handheld display. It picks up the radio signal, which comes from the transmitter on the right, black box on the right. And also what's not pictured is the USB base station, which can also pick up the signal from the air and transmit it into your computer, the PC computer, for logging and graphing. I'm going to show you another screen that shows an example now of what the display software would look like on your PC. If you look, channel 1, channel 2, channel 3, those can represent different load cells that you have. You can also, for instance, take channel 1 plus channel 2, do a math function, and have it equal a channel 3. So you can also perform some summing functions while looking at individual inputs. So it's very valuable software for you to have. In addition to this, there are other modules that we have that connect with this that can provide analog output or serial type outputs as well. So it's a very nice product for you.